Hey there, chemists. In this last lesson, we are just going to look at a few problems that help us practice non-equivalency in hydrogens, and then some reaction problems, and then we'll close with just some common patterns that we see in NMR spectra. So first off, there's a couple of new vocabulary words for today. What constitutes different hydrogens? We can classify hydrogens as being equivalent or non-equivalent in different ways. If they're in exactly the same environment and they classify as what are called homotopic, we can tell that by replacing one of the H's with just some arbitrary other group X to make it different. And if that doesn't change anything about the molecule, those are what count as homotopic hydrogens. For example, in methylene chloride or dichloromethane, these are two homotopic hydrogens. Homotopic. If I imagine changing one of them to just something else, I'll just shade it a different color, as opposed to making the other one shaded. Those two compounds are exactly the same. So we say that those two hydrogens are homotopic of each other. However, if that's not the case, such as I'll pan over to this molecule here, these two hydrogens are identical to, are in the same environment in this molecule, but we call them enantiotopic because you can imagine replacing one of them with a different group, and then if you replaced the other one, those things would count as enantiomers. That was not true for the first compound. So let's go back and look at the rest of these in this row and see how this works. Which of these are homotopic, which of these are enantiotopic, which of these are neither of those two. In cyclopropane, the two hydrogens there, if I imagine replacing one of them with a different group, I'll just shade it differently, as opposed to the other one, those two molecules would be the same. So these are also considered homotopic hydrogens. In the cyclohexane molecule right next to it, I'll do the same thing. Let me pretend I have a different group where one of those two hydrogens is, as opposed to here. Well, those two molecules, if that was a different group, if the shaded H was like an X or something, those would be the same molecule. So those are also homotopic. We already did this alcohol. How about the last one? This one is a little bit trickier. I'm actually going to draw two different structures to really drive home what we're doing here. Let's pretend I replace one of these two H's they're asking about with a different group, and then I'll redraw the molecule. Let's just call it an X. Now I'll pretend I'm replacing the other H with that different new group, an X. And the key is, how do these two imaginary structures compare with each other? Are they the same? Well, then those H's would be homotopic. Are they enantiomers? Well, then those two things would be enantiotopic. In this case, it's neither of those. These are actually diastereomers of each other. These two phantom structures by replacing one of the H's with an X group. So that means that these H's are diastereotopic. If you guessed that, you were right. So those are the three different categories we have. I would like you to hit pause and try the remaining 5 structures down below. There's a pair of H's highlighted in each. Would you consider them to be homotopic, enantiotopic, or diastereotopic? Hit pause, try it, come back, see how you did. Okay, let's check. The next one, the first one in the second row, these are diastereotopic, just like the last one we did together. I think the easiest way to see that is to draw out the two imaginary compounds. Here's your dimethyl cyclopropane. Let's make one of those H's just an X, and then let's draw what it would be if we made the other H and X. Yep, those are diastereomers of each other, so the H's have this relationship of diastereotopicity. Right next to it, however, these are homotopic. That might be difficult to see, but if you replace one of them with an X group and then compare it with a structure where you replace the other one with some other X group, just saying X to make it different from H and everything else we have, those are actually the exact same compound. If you draw them out, you'll see that to be true. Same with this butene molecule. Those are homotopic hydrogens. But when we get to this dichloro compound, these two H's that are a little bolder than the others, those are the ones they're asking us about, If I replaced this one with an X versus this one with an X, those two imaginary structures would be diastereomers of each other. So those are diastereotopic H's. And then lastly, this chlorofluorocarbon, those are enantiotopic. I'll draw this one out. Imagine replacing one of those H's with an X, or replacing the other one with an X. Remember, this is an sp3 carbon, so it has direction, so I'm using a dashed line for one and a bold for the other. Those will be enantiomers of each other, so we say that the hydrogens are enantiotopic. These are just ways for chemists to describe a pairing of hydrogens when you're looking at how they show up in an NMR spectrum. They sometimes end up becoming non-equivalent because of other aspects of asymmetry in a molecule. So it's just some language. Okay, the rest of this page are just a couple of more challenging questions related to structure determination. Here's a reaction problem. We've been doing a lot of this lately. What happens when you ozonize a compound? Here's an unknown structure A, and we're turning it into structure B. Here are their proton NMRs. Luckily, they give us molecular formulae. Whenever you have to do a structure determination question, a good starting point is just figure out the degrees of unsaturation. So the degrees of unsaturation, remember, is carbons minus 1/2 of hydrogens, plus halogens minus nitrogens plus 1, tells you the rings and pi bonds. So for compound A, we have 10 minus 1/2 of 16 plus 1, and I get 3. So I have 3 rings or 3 pi bonds or a combination of each. I'm going to do that for this product, C5H8O2. That would be 5 minus 1/2 of 8 plus 1, and that's just 2. 2 rings or 2 pi bonds or 1 of each. I also noticed that the formula lost a whole bunch of carbons. No, it didn't. Think about what ozonolysis does. It breaks pi bonds to make carbonyls. We must have formed 2 of compound B for every 1 of compound A. And that makes sense. You keep all 10 of your carbons, your 16 hydrogens, and you gained 2 oxygens. So that's highly suggestive that we have 2 new carbonyls in our structure for each one of these. So each compound, each structure has 2 CO double bonds. So, and since I know a little bit more about compound B, just that information alone, I'm going to start by looking at the spectrum for B, and then we'll go backwards and check and make sure A makes sense. The spectrum is really simple. This must have a lot of symmetry. There's only 2 signals. They're singlets, so no splitting. That means no neighbors, no vicinal neighbors. And the 1-to-3 ratio must mean the integration is 1-to-3. Remember, NMR just tells you relative ratio. It doesn't tell you the absolute, but you can figure it out really quickly. If there's a total of 8 H's and it's a 1-to-3 ratio, that must mean it's the same thing as a 2-to-6 ratio, so that they add up to 8. So here's a 2 hydrogen signal and a 6 hydrogen signal. So what could explain these signals? Well, the 2 hydrogens must be a CH2, apparently with no neighbors. I don't know what it's connected to on either side, but I have a methylene in the middle of my molecule. And then 6 hydrogens? Well, you can't have 6 all on the same carbon. So I probably have 2 methyls in exactly the same environment. And then since the spectrum only goes up to 4 on the left of the x-axis, I must have ketones. I don't think I have aldehydes. Remember, ozonolysis makes ketones and aldehydes. Aldehydes show up way to the left in like 9 or 10 parts per million. We are nowhere near that, so these must be ketones. So as I'm drawing my like pieces of the puzzle, I think we have 2 ketones. So here's our pieces. I have a methylene, a ketone, another ketone, a methyl, and a methyl. I just have to put those together. I always think about this in terms of what are your bookend pieces, the end caps, which would be the methyls, and then what pieces can go in the middle, 2 carbonyls and a CH2. And there's only 2 ways you could do it. You could either have a methyl, a carbonyl, a CH2, and a methyl, or you could have a methyl, a carbonyl, a CH2, another carbonyl, and another methyl. And then just check which one matches the NMR. Should be pretty easy to figure out. It must be this more symmetric one. This has no neighbors for any of the signals, so I would only see singlets. So it can't possibly be this structure. It must be this structure. I'll put a box around it, and we can confirm it by checking what structure A should look like. So what would A be? Well, it's got to be 10 carbons and 16 hydrogens. Again, a really symmetric NMR, a 1:3 ratio. Well, if it adds up to 16 H's, that must mean this is a 4 hydrogen signal, and this is a 12 hydrogen signal. I'm just scaling up the ratio. That's still 1:3. What would the structure look like if it gives me this diketone? And hang on a second, it has to give me 2 of those diketones. Well, they would have to stitch together and come from a ring with 2 pi bonds in the ring. Remember how ozonolysis works. You start with an alkene, you break the pi bond, and you get a carbonyl on each side. In this case, it's ketones. So we have something kind of like this, but they must be tied together in a ring. So what I'm going to do is I'm going to draw my compound B again. And I'm going to draw a second one right next to it. And just try to visualize, like, how do these go together? Well, if I, like, turn it upside down and imagine them being stitched together, aha, I think I can tell it must have come from a 1, 2, 3, 4, 5, 6 membered ring with 2 alkenes on either side and methyl branches coming off of all of them. Let me just move this one out of the way, and then let's draw that as a structure. So I have a cyclohexadiene with methyls everywhere. Let's check the NMR and make sure. Nothing above 3. Yeah, all my H's are in the allylic range, 1 away from a pi bond. So they're in like the 2s and the 3s. That makes sense. You've got 4 identical H's with no neighbors that would cause this signal. And then you've got 12 more identical signals from the 4 methyl groups. So those are your structures, A and B. Lastly, we've mentioned this many times throughout this unit, how to look for what we've been calling red flags or just common patterns in an NMR. And you can recognize them by just looking at the coupling of a couple of signals and how they're split and what their integration is. For example, here's an ethyl group. An ethyl, a CH2, CH3, will always give you a 2 hydrogen signal that sees 3 others, and 3 others that see those 2. So the quartet tells you the 3 neighbors, the triplet tells you the 2 neighbors, and then the integration kind of matches. So I want you to hit pause again and see if you can figure out what you would expect these 3 other groups to look like in a typical NMR. Not even necessarily where they show up, but what pattern would you see for an isopropyl, a methoxy, and a para-disubstituted benzene. Sketch that and see what you get when you come back. Okay, we've seen all of these before, so hopefully just drew on things you've seen in class. An isopropyl group will always have a large doublet integrating for 6, and then paired, coupled with a small multiplet, like at least a septet. And that's because if you think about what an isopropyl group looks like, you have 6 identical H's for the 2 methyls and then 1 other for the multiplet. The splitting of the multiplet and the location of the multiplet depends on what else is attached. If it's an O isopropyl, then this signal is certainly shifted farther to the left, but it depends on what's there. Speaking of location and where it is in the spectrum, what's a methoxy look like? An OCH3? Well, that's definitely a singlet. You will just have a 3 hydrogen singlet. You can usually predict the location. It's probably between 3 and 4 ppm on the x-axis because it's on a carbon attached to an oxygen. That electron withdrawing oxygen will just put it in that position usually. And lastly, a para-disubstituted benzene. That means a 1,4 disubstituted benzene. So you'll have 2 H's on either side of the ring. That will count as 1 signal. And you'll have 2 others that will count as the other signal. And that's a pair of doublets, each worth 2 hydrogens, provided that it's not a completely symmetric disubstituted benzene that you have something here and something else here. And the location is usually predictable too. It's usually in the 7s, up in the 8s, give or take. But those are just a couple of common patterns that we can look for and then immediately draw them in a structure. Okay, that wraps up this unit on structure determination. Thanks for watching.